Welcome to this little tutorial on evidence lower bound. Evidence lower bound or ELBO is used as a loss function when doing variational inference. The objective of this tutorial is to show where this derivation comes from as well as develop the intuition about its components. Here I am showing you a latent variable model and Bayes rule to obtain the posterior distribution of the latent variable z. As you probably know that even though Bayes rule is very elegant and intuitive, it is the denominator that is the culprit. It is a culprit because in high dimensional spaces it translates into an intractable integral. Now while we are here, I want you to pay attention to the fact that I have used different colors for the parameters of likelihood, prior, posterior and evidence. Reason I have done so is to indicate that these distributions could belong to different families and have different number of parameters. Symbol uses still theta, but colors should help you appreciate this fact. That said, one remedy to get around this problem of not able to compute the posterior because of the normalizing constant is to use variational inference. Variational inference suggests us to use another distribution as an approximation to the posterior. I'm using the symbol Q for this approximation distribution that we would pick and phi to represent its parameters. Now when we will choose Q, we would select one for which we can compute the normalizing constant and we should be able to sample from. So our goal is defined, that is to simply approximate the intractable posterior distribution with a simpler distribution. But we must still learn the parameters, that is phi in this case, and we would do so by using an optimization procedure. That said, an optimization procedure requires a loss function, that is we need a way to compute the dissimilarity between the ground truth and the predictions using the parameters we are learning. But how to quantify the dissimilarity between two probability distributions? This is where we would use something called KL divergence. And it is also a prerequisite to understand ELBO. If you already know what KL divergence is, then all is well. But if you do not or have some gray areas, then I have a tutorial on that as well. In that tutorial, I give you the intuition behind it as well as the derivation. So check it out if need be. Assuming you do understand KL divergence, our goal has now morphed into the task of minimizing the reverse KL divergence between P and Q. But I wish it was that simple. The trouble we have with KL divergence in its current form is that we cannot compute the denominator. Denominators seem to be always the troublemakers for us. You should be able to see that in the denominator we have the true but intractable posterior, which is what we want to approximate. So how to get around it? Well, the remedy is simple. When you are stuck with a big complex problem, try to first divide it into multiple parts, hopefully simpler independent parts, and maybe then we will find a way to solve the parts and thereby get our solution. And we will do exactly that. I'm going to start simplifying the KL divergence by factoring it into components. So far nothing has changed. The first simplification is to show it as a difference of expectation. Division just got changed into subtraction because we are using a log function. Now focus only on the second component of this equation. I am rewriting it using Bayes rule. Here is a little reference if you are not seeing how I did that. The numerator is nothing but the joint distribution which factorizes into likelihood and prior. Still focus on the second component. I have now split it further. Focus on the third component this time, the last one. You would see that it is an expectation with respect to z, and when I expand it to its integral form, it would be like this. Now I have simply moved the part that does not have z outside the integral, and this is the final simplification. This is possible because integration of any density function, q in this case, would equate to 1. So our integral goes away. This simplification has indeed revealed something very interesting. This third component is the marginal log likelihood or the log evidence. The word marginal is important as it tells you that it is the total probability taking into account all hidden variables and parameters. Now in this problem of ours, we cannot compute it because we do not have its analytical form. Nevertheless, this equation is revealing that log likelihood and KL divergence has a relationship. I said it is interesting reveal because most of the time you do maximum log likelihood estimation. So you can see the connection between KL divergence and log likelihood here. I have now rewritten it so that log evidence is on the left side and the signs of other terms have been adjusted accordingly. So we have log evidence that we cannot compute, we have KL that we cannot compute, we have already done some simplification. Therefore, now is the best time to get little creative. First, let me assign two labels to the right hand side. I am labeling the first two terms as component 1 and the third term as component 2. What is sure is that I cannot compute KL, the second component. We know this from start. But there is an interesting property that I know that KL divergence possesses, which is that it can never be negative. That said, now I am going to make you a proposal to get rid of KL divergence from here. And you would react by saying that in that case, at minimum, this equality has to go away. And I agree. So we would rewrite the marginal log likelihood as this, which is in simple English equal to saying that marginal log likelihood would be at least this quantity. It would be more if KL is greater than 0. And this is really the reason why we call this portion evidence lower bound. It is the lower bound on your evidence. This all being said, you would feel that now I have cheated you by getting rid of component 2. But I still have one more argument to make that should help you come to peace with this formulation. Let's focus on the top part again. The trick here to appreciate is that if I could maximize the component 1, which is ELBO, then indirectly I'll be minimizing the component 2 for this equality with marginal log likelihood to hold true. Remember, I said that marginal represents that probability after taking into consideration all parameters and hidden variables. We cannot compute it in this case, but we know that it will not change. And so we have found a way around our KL divergence. We'll be minimizing it, but indirectly. We'll be minimizing it by maximizing the ELBO. Now we can leave it here. This is actually a good formulation already, and you will find this in the literature as well. But we can further simplify it as well, and that would reveal some other interesting parts as well. So let's do the final simplification. Nothing has changed so far. It is the same ELBO. Focus again on the second term as I'm going to simplify it. This second term is the joint probability of x, and our latent variable z can be expanded into two factors. Because we are in the log scale, we are doing addition and not multiplication. I have applied the product rule of probability on joint distribution. It is not more than that. Now I am simply moving the terms around. Nothing has changed in the equation, and I have this final formulation. This is the representation that you would find in the literature, and it tells us that ELBO can be seen as consisting of expected error in the reconstruction and KL divergence between approximate, posterior and prior. Reconstruction because here we are getting x conditioned on z, so we will be reconstructing x. KL divergence because it is the expected log likelihood ratio between two distributions. Do not confuse it with the KL divergence that we started with. That was a KL divergence between the approximate posterior and the true posterior. This is between approximate posterior and the prior. We know the prior and we will learn the approximate posterior. That said, I want you to note that we picked our approximation Q such that it was a conditional distribution. That is, it was for Z but conditioned on X. As such, we could have picked Q for just Z. That is, it does not need to be conditional. And all the derivations that I showed to you would still remain the same. So you can see, you can compare these two equations. You will see the only difference is that in the second case, I have selected a distribution such that it is not conditioned on X. So we have our loss function under control, and now all we need are the algorithms. There are two algorithms that are most famous for variational inference. The first one is expectation maximization, and the second one is the variational autoencoder, which is based on neural networks. And this brings us to the end of the little tutorial. I hope this tutorial was helpful and you were able to see where ELBO comes from and what it represents. If you have questions and doubts, please do let me know in the comments and I would try my best to answer them. With that, thank you for your time. Bye bye.